Hello, we are Team Smart Breaker. This video will provide a project review of our Smart Breaker system. The Smart Breaker panel was born from the idea of improving an often overlooked component of a household. We wanted to create a breaker system that allows a homeowner to assess a trip breaker with no guesswork involved. To accomplish this, we created a system that allows a homeowner to easily identify a down circuit and then gives them the ability to bring the circuit back up again without having to blindly flip switches on the breaker panel. This is done through a simple graphical user interface that is easy to use and that displays vital information to the homeowner. This GUI is accessed on a web application that can be used wirelessly. With this, it is extremely easy to identify the trip breaker and set it back up again with no fumbling around in the panel. There are also other features to the panel, but these will be discussed later in the video. Modern household breaker systems are designed so that a homeowner can blindly flip switches in the breaker box. If a single circuit goes down, the homeowner may not know which switch in the breaker box is associated with the outage, and could easily flip another switch instead of the desired one, especially if the switches are labeled incorrectly. Along with this, in certain households, breaker panels can be hard to reach and difficult to maneuver. Our system will function wirelessly, creating a safer, more manageable troubleshooting environment. Our project hopes to address all of these problems. This is a general overview of the entire system, including the electrical and structural components. These components are as follows: a Raspberry Pi that hosts a server and acts as a web application, 2 TIVA microcontrollers that control operation of each breaker, a current transformer, a pull-up resistor, a DC power source, 2 solenoids, and finally the relay. These are more pictures of the actual build of the system. As can be seen, each component is connected as specified in the drawing shown in the slide before. The breaker itself contains 2 solenoids, one acting as the main actuator that opens and closes, and another that is a latch that holds the breaker in place. The latch allows us to consume power only when opening or closing the breaker, eliminating heat dissipation and lowering our power consumption. The pull-up resistor is used to step up the 3.3 volt I/O of the TIVA to the 5 volts required to turn the relay on and off. This is unnecessary, and in a final product, the relay would have a control voltage of 3.3 volts to eliminate this circuitry. The 2 circuits on the right show the pull-up resistor modeled in LT Spice, one showing the high state and the other the low state. The current transformer is used to actively see what current is being pulled by any circuit in real time. This current transformer has a range of 0 to 100 amps. The first section of the transformer is converting the current into a voltage because the ADC pin on the TIVA reads voltages with respect to ground. This is done by using the 30 ohm resistor in parallel with the CT. The second section of the circuit is what's called a small voltage rectifier. We must rectify the signal because the ADC on the TIVA only reads positive voltages. We had to use this specialized rectifier because with a normal rectifier using a diode, the voltage must read above the threshold voltage of the diode, which is typically 0.7 volts. The final component of this circuit is the smoothing capacitor, which is used to ensure that the output voltage is as close to DC as possible. There is also a moving average, which is utilized in the software to guard against any transient spikes that may be caused by inductive or capacitive loads. This ensures that the breaker will not trip if there's a spike in current for a specified period of time. In software, there is a simple equation that reverses Ohm's law from the series resistor to give us the actual current value on the line. This is the Simulink file that is built onto both of the TIVA microcontrollers. The TIVA communicates serially with the server on the Raspberry Pi via UART. The TIVA receives an input packet from the server. This input goes through a finite state machine to determine the operation of the breaker, and then a voltage is applied to GPIO pins to activate the different solenoids. In the case of a fault current, a packet is sent back to the server to notify a change in operation status. From here, a moving average block was created to find an amperage that would be used to determine the threshold at which to trip the breaker. This average is sent to the finite state machine, and if it is higher than a specified threshold, the breaker will trip and it will send an error signal. The server will always see an operational status unless it receives the fault current signal, in which a not operational status will appear until the user addresses the problem. This is the graphical user interface that is accessed by the user. It was created through Python and its HTTP server module that provides the backend for a simple but effective server that also acts as our web application. This server was located on the Raspberry Pi, which communicates via UART to the Tiva microcontrollers for breaker operation and status updates. The GUI provides the operation status of each breaker, options to manually open or close each breaker, and also provides different modes of operation. For example, vacation mode allows the user to turn off multiple breakers that would save power during an extended time from home. Storm mode allows the user to turn off certain breakers that serve devices that may be susceptible to damage during a strong thunderstorm. Different modes could be added with time. Along with this, the option to change a device at a certain breaker is also provided through the use of QR codes. As can be seen, multiple devices can be added to each breaker and can be moved from one to another. In its current state, this is done by uploading files to the server from the device that is accessing the web app. This was not the original plan, but this will be discussed in detail later on in the video. Security measures were also implemented, as when initially accessing the web app, a username and password must be provided. The project performs as intended, but not without hiccups. This project does what it's supposed to, but it has issues that have caused the group to deem it as an alpha version of what could be provided to customers if this were to become a real product. With more time and readily available equipment from the ECE Senior Design Lab, this project could adapt into something absolutely considerable for real-world use. There could be notable improvements made to the software side, allowing users to set times for when a circuit turns on and off, as well as being able to design auxiliary devices that connect to the network and send information via the server. Overall, we were satisfied with our project's performance, even though there is still much room for improvement. A strength of the project is that it successfully addresses most of the problems that we defined for current breaker panels. The breakers can be controlled mobilely from a web application with relatively few issues. The breakers reliably trip in the case of an overcurrent and don't trip when they shouldn't. The user can access various information without having to physically interact with the breaker panel itself. Overall, the breaker operates as it was mainly intended to. A weakness of the project was not being able to fully implement the QR code functionality as we had envisioned. The initial idea was to give the user the ability to change devices at a given breaker location by scanning an associated QR code with their phone camera. In practice, however, we had to resort to uploading files from the device accessing the web app rather than scanning in real time, as time constraints did not allow for configuring the program to get through different device security measures. Another weakness of the project was not being able to fully see breaker operation statuses update in real time. It was thought that extensive measures such as polling would have to be implemented on the server in order to accomplish this, but Dr. Groff did mention there could potentially be built-in functionality within HTML that could have been our solution. Now we will show the full demo of how the system works. When first accessing the app, the user must provide a username and password. To begin, both breakers are closed, which is what we see happening here. And at a glance, all breakers appear to be operational. Next, we activate storm mode, which in our case opens both breakers. We then proceed to close both breakers again, and then perform vacation mode on breaker A, which opens the breaker. Then we close again and proceed to check CT functionality. A fan is turned on, which is connected to breaker B, and we see that it stays closed, indicating that a trip has not occurred and that the breaker is operational. Next, the toaster connected to breaker A is turned on, and this will trip the breaker. This is verified here. We can now see that the breaker status for A has changed to not operational. Once we close the breaker, it goes back to operational. Now we'll look at QR code functionality. As stated earlier, The QR codes must already be available on whatever device you're accessing the app from, which in this case is a laptop. It contains codes for multiple devices that can then be assigned to different breakers. We attach a dryer to breaker A and then a light to breaker B. We then decide to move the dryer from A to B, which removes its association with A. This has been Team Smart Breaker. Thanks for watching.